For the last few years, the entire AI revolution has felt like it's all about language. But what if that's only half the picture? Fei-Fei Li, who's basically one of the godmothers of AI, makes this powerful argument that the revolution we're in right now is fundamentally incomplete. We're about to move from an AI that just reads text to an AI that actually understands the physical, three-dimensional world we all live in. And to really get why that is such a massive deal, we first have to look at where AI stands today.
So just take a look at the state of AI right now. We've gotten incredible at building models that have totally mastered language and can recognize what's in a picture. But the second you ask them to reason about 3D space, about physics, about how objects actually bump into each other and interact, their capabilities just fall off a cliff. This uneven intelligence means that even our most advanced AI is, for all practical purposes, blind to the physical world. This isn't just some small gap, you guys. It's the missing link.
And this leads to a pretty wild question, doesn't it? How on earth can an AI write a beautiful sonnet or debug code or even pass the bar exam, but it can't grasp the basic physics of a simple doorknob? How it turns, what it's attached to, what it does. This is what's being called the physicality gap, and it is the central challenge we've got to figure out.
To really wrap your head around why this gap exists, you have to get comfortable with this one powerful idea. The map is not the territory. The philosopher Wittgenstein once said, "The limits of my language mean the limits of my world." Well, for today's AI, that's become a really dangerous limitation. Language, you see, is just a flat, symbolic representation of reality. It's the map. It is not reality itself.
Think of it like this. Language models, or LLMs, are like that flat piece of paper on the left. It's just the raw material, the information, all symbolic and one-dimensional. But spatial intelligence, well, that's something different. It's like knowing origami. It's the understanding of geometry and structure and physics that lets you take that flat material and fold it into something with shape and purpose and function. See, real intelligence isn't just having the paper, it's knowing how to fold it.
So here's the crucial part. We absolutely have to unlock this third dimension of intelligence. We need to teach AI to go beyond the flat map of words and finally start to understand the folded, complex, messy territory of the physical world.
And a famous moment in science illustrates this idea perfectly. When Rosalind Franklin took her X-ray image of DNA, what she got, the data, was just a shadow. It was a fuzzy cross on a flat, two-dimensional picture. Now, that was a vital piece of the puzzle for sure, but it wasn't the answer. The data was just the shadow, not the object casting it. The real breakthrough, the genius of it all, required a cognitive leap, and that leap is called spatial reasoning. It's what Watson and Crick did. They looked at that flat 2D shadow and used it to deduce the hidden three-dimensional structure of the double helix. That ability to infer a complex reality from limited, flat data is exactly what we're now trying to build into our AI systems. And let's be super clear here. This is not about just processing more data or having a faster computer. It is a fundamentally different kind of intelligence we're talking about. It's about intuition and inference and, well, what you might even call a leap of imagination. And that is something our current language-based AIs just weren't built to do.
So, how in the world do we make this leap happen? Well, a new model from a company called World Labs, called Marble, is designed to do exactly that. Get this, you give it a simple 2D input. It could be a photo, a quick sketch, or even just a text prompt, and it acts like a creative engine, inferring all the invisible dimensions. It doesn't just spit out another picture, it generates a fully interactive, explorable 3D world with all the logic of space and light and texture built right in. It's literally turning flat pixels into three-dimensional voxels.
Now, this ability to just generate entire 3D worlds on demand, well, it has a massive impact. It lets us create something that sounds like it's straight out of science fiction, a training ground for AI. You could basically call it the Matrix.
The first place we're seeing this hit is the economy, especially in creative fields like special effects, video games, and architecture. This tech can speed up the process of visualizing a scene by 40 times. I mean, think about that. Complex scenes that used to take days of painstaking work can now be mocked up and explored in minutes. Suddenly, the bottleneck isn't the technical skill anymore. It's just the speed of human imagination. But making cool movie scenes is really just the warm-up act. The true North Star, the ultimate goal for this technology, is robotics. And this chart right here shows you why that problem is so incredibly hard. Just look at the insane jump in complexity, what's called degrees of freedom, from a chatbot to a self-driving car, and then that almost vertical leap to a humanoid robot that has to deal with our world.
A chatbot can hallucinate, and who cares? If a robot hallucinates about physics, it crashes and burns. The biggest problem for robotics has always been a massive shortage of data. I mean, a language model can just feast on the entire internet, right? But there's no internet of physical interaction for a robot to learn from. All that real-world training data we can get, it's just the tiny tip of this iceberg. It's scarce, it's expensive, and frankly, it can be dangerous to collect.
And this is where the solution is just so elegant. If you don't have enough data from the real world, you just generate an infinite amount of synthetic data. These world models create these perfectly safe, risk-free simulated gyms where robots can train for millions of hours. They can learn to walk and grab and navigate in this matrix long before they ever take a single step in our world.
Of course, as we build these unbelievably powerful systems that can see and act in the world, it brings up a huge question about who's in charge, about governance. And this brings us to what might be the single most important component in all of this, the human validator.
Fei-Fei is absolutely emphatic on this point. You cannot outsource trust to a machine, period. As this diagram shows, the entire stack of technology, the algorithms, the data, all the computing power, all of it has to rest on a foundation of human agency and human trust. The goal has to be to serve people, which means we, humans, have to be the ones who build, validate, and ultimately oversee these systems.
This quote really just nails the entire shift we've been talking about. This is a fundamental turning point in the history of computing. We are leaving the era of an AI that just reads and processes human knowledge, and we're stepping into a brand new era of an embodied AI, one that sees and acts and interacts with the physical world right here alongside us.
So what kind of mindset does it take to navigate this completely new world? Well, you could call it the economics of fearlessness. In times like these, when everything's changing so fast, all the easy, certain jobs get crowded. The real value, the exponential innovation, is found way out here in what's called the fearless zone. It's where you embrace high uncertainty and you go after the hard problems that everybody else is too scared to touch.
And that really leaves us with one final thought. We are standing right at the doorway of a new era, one where our digital creations are about to step off the screen and into our physical reality. The real question is, are we prepared to be fearless? Are we ready to run towards that uncertainty, into that uncharted territory of spatial intelligence? Because that's where all the magic is really about to happen.